Welcome to Books in Focus podcast.
The show that gives you a shortcut to being truly well-informed. Have you ever noticed how your phone seems to know exactly what product you might like, or your navigation app predicts your commute time almost perfectly? Or maybe your email just magically sorts out spam without you lifting a finger?
Yeah, all the time.
These aren't magic tricks. They're the quiet, powerful work of something called machine learning.
That's right. What was once a concept discussed only in, specialized labs and by tech giants is now deeply woven into our daily lives. It influences everything from how we consume information to how we manage our health.
And that's exactly our mission today. We're going to pull back the curtain on machine learning, cut through all the technical jargon to help you truly grasp its core concepts.
Understand how these systems actually learn.
Exactly, and why this technology is becoming so incredibly pervasive.
Yeah.
We're drawing our insights from a comprehensive new textbook, a resource specifically designed for, well, tech enthusiasts, college students, junior managers.
Yeah, the authors, they're experienced professionals, strong backgrounds in AI and ML. They wrote this because they noticed that machine learning concepts, while really powerful, aren't as widely understood as they probably should be. They really want to demystify it for a broader audience.
Okay, so to kick us off, the source material highlights a core idea right away. Machine learning imbibes the philosophy of human learning. What does that even mean for a machine? How does that work?
That's a great question because it's truly foundational. When we talk about how machines learn, it's actually surprisingly analogous to how we humans learn.
Okay.
Think about a baby learning colors. Their parents point to a red ball and say red, right? And over time, the baby connects the word to the object. Or maybe a student learning grammar rules from a teacher. Our sources call this guided learning.
So for a machine, this guided learning means it's learning from experts, which in the world of machine learning translates to learning from past labeled data. You feed the machine examples where the answer is already known, and it starts to see the patterns.
But it's not just about being taught, is it? We also learn by doing. A baby learns to walk by, falling down a lot.
Yeah, lots of trial and error.
Or an adult learning to drive. You make mistakes, you adjust, and you start forming a kind of checklist of things to do and not to do based on experience.
That's learning by self for humans, and machines truly mimic this. They learn from the mistakes they've made in the past. So this whole human learning philosophy, it translates directly into, what, 3 basic steps for machines?
Pretty much. First, there's data input. Think of it as the machine soaking up all that past experience, everything it's seen before.
Okay, the raw material.
Right. Second comes abstraction. This is where the machine sort of boils down that input data into core patterns or rules. A bit like our brain forms a mental model from lots of different examples.
Right, finding the essence.
Exactly. And finally, generalization. That's where it forms a framework from that abstracted representation to make future decisions, applying those learned rules to new, unseen situations.
It's incredible to see these abstract concepts come to life in the real world. Machine learning isn't just about predicting, the next hot real estate market or recommending what product you should buy.
No, not at all. Our sources really highlight its utility in some truly diverse and impactful areas.
Like?
Absolutely. Take healthcare, for instance. It's assisting medical practitioners in diagnosis. Our sources mention its ability to help spot breast cancer cells maybe a year before diagnosis.
Wow, that's huge.
It's a massive leap forward. It's also being used to optimize energy consumption, playing a vital role in our efforts for a, green Earth.
And on a more everyday level, it's the intelligence behind things like handwriting recognition.
Yeah, the U.S. Postal Service uses that.
Right, or personalizing your newsfeed on platforms like Facebook so you see content that's most relevant to you.
And what's truly fascinating is how the big players have taken this technology to new heights. We've seen IBM's Deep Blue beating chess champion Garry Kasparov.
A huge moment.
Monumental achievement, really captured public attention. Then there was IBM's Watson, famously beating human champions in Jeopardy.
Which was just mind-blowing to watch.
Totally. And Google have been consistently innovating with projects like Google Brain, Sybil, Waymo for self-driving cars, and AlphaGo, which mastered the ancient game of Go. These aren't just cool tech demos. They're pushing the boundaries of what machine learning can do, showing just how deeply woven it is into, well, all walks of life now.
So with all these incredible applications, before you even think about building such a system, our sources highlight a critical first question. Should we even use machine learning to solve this particular problem?
That's step zero, really. Not every problem is a good fit.
Right. And once you decide it is, you need to understand the type of problem you're dealing with. Our sources give a great example to distinguish between two core types. Predicting whether a tumor is malignant or benign versus predicting the price of real estate.
Two very different goals.
These two problems require fundamentally different approaches.
And this brings us to the core distinction: classification versus regression. When you're predicting which category or class something belongs to, like malignant or benign, a yes, no, or a red, blue.
So label.
Exactly, a label. That's a classification problem. The output is a categorical variable.
But if you're predicting an absolute numerical value, like a specific price for real estate, or perhaps how many items will be sold next quarter.
Then that falls under regression. The output there is a real valued number, a specific quantity.
Okay, classification for categories, regression for numbers.
Yeah.
Makes sense.
And sometimes the goal isn't to predict a specific outcome at all. Sometimes you just want to find hidden patterns or group data without any prior labels. This is where unsupervised learning comes in.
Ah, okay.
Our sources describe it as analyzing unclassified information to discover hidden knowledge. The algorithms basically work without prior training, just looking for structure.
A great example provided is grouping research papers by subject area like statistics, computer science, or machine learning based purely on their content, without being told what they are beforehand.
Right. The machine identifies those groupings all on its own, seeing connections we might miss just by looking.
Okay, so once you've identified the problem type, classification, regression, or maybe unsupervised, the real work begins with the data itself. The importance of data in machine learning, well, you can't overstate it.
Absolutely not. You need to understand your data, starting with its types. Quantitative data, which is measurable like height, weight, price,
Numbered.
right, numbers, versus qualitative data, which is categorical, things like good, average, poor performance, or names and ID numbers.
Got it.
Knowing your data is absolutely key. This means understanding its structure, specifically which attributes are numeric and which are categorical. Our sources mention that a data dictionary, basically a metadata repository, is ideal for this.
What's that do?
It provides detailed information on each attribute, like its meaning, its type, what values are allowed. It's like a map for your data.
You know, when you're just looking at a raw spreadsheet full of numbers, it can be really hard to get a feel for the data, right?
Oh, definitely. Just rows and columns.
Our sources highlight a simple but remarkably powerful tool that gives you an instant snapshot of numeric data distribution. Box plots.
Ah, yeah, box plots are great.
They're called an extremely effective mechanism to get a one-shot view. They concisely show the minimum, first quartile, Q1, median Q2, third quartile, Q3, and maximum.
And crucially, they clearly highlight any outliers.
Right. Those weird points way off on their own, which could be errors, or maybe something really interesting.
Exactly. And for exploring categorical data, two-way cross-tabulations are very useful. They help us understand the relationship between two categorical attributes.
How so?
For instance, how car cylinder numbers might vary with the model year, or maybe the car's origin. It's like creating a simple table that shows the counts or percentages of different combinations.
Okay, seeing how categories relate.
Precisely.
So after exploring your data, getting a feel for it, it's time to train and validate your model. The most common approach, especially in supervised learning, is the holdout method.
Right. Typically, you use, say, 70–80% of your labeled input data for training the model.
Okay.
And then you hold back the remaining 20–30% as test data.
And that test data is super important, right?
Absolutely crucial. It's the unseen data the model has never encountered before, and it's what we use to truly evaluate its performance. How well does it generalize?
And the split.
It's random.
Yeah, the division between training and test sets is done randomly.
Yeah.
That's to ensure both sets are, similar and representative of the overall data.
Okay. Now, what if you don't have a huge amount of data? Is holding back 30% always feasible?
That's a great point. For an even more robust evaluation, especially if you don't have a massive data set, K-fold cross-validation is widely popular, particularly tenfold cross-validation.
How does that work? With tenfold, you divide the data into 10 equal parts, or folds. Then, the model is trained and tested 10 different times.
10?
Yeah. Each time, a different fold is used as the test data, and the other 9 are used for training.
Oh, I see.
The performance is then averaged across all 10 runs. This gives you a much more reliable and stable estimate of how well your model will likely perform in the real world. It's like having multiple rounds of quality control built in.
That sounds much more thorough.
It is. And then there's also bootstrap sampling. That's a technique that randomly picks data instances with replacement.
With a replacement, meaning?
Meaning the same data point can actually be picked multiple times when creating a single training data set. You create multiple training data sets this way.
Huh. Why do that?
It's another powerful way to build robust training sets and, importantly, to understand the variability or stability of your model's performance.
Okay. Now, when you're training these models, you often run into common pitfalls. The sources mention underfitting and overfitting.
Ah, yes, the classic struggle. Overfitting happens when a model learns the training data too well.
Too well. How can it learn too well?
It means it learns not just the underlying patterns, but also the noise, the random fluctuations, maybe even specific outliers in the training data.
Okay.
It's like that student who memorizes every single detail of one textbook, including like typos and footnotes, and then completely struggles to apply the concepts to new, slightly different problems. An overfit model performs great on the data it was trained on, but poorly on new, unseen data.
Right. It didn't really learn the general concept.
Exactly. The opposite is underfitting. That's where the model is too simple. It doesn't capture the underlying patterns in the data at all, and it performs poorly on both the training and test data.
So neither extreme is good.
Not at all. Finding the sweet spot between these two, often called the bias-variance trade-off, is the central tension in machine learning. It's about finding a model that's complex enough to capture the real patterns, but not so complex that it's fooled by random noise.
That sounds challenging.
It highlights why building a truly robust model is an art, not just a science. You're constantly tuning and adjusting.
So once a model is trained, we need to measure its performance. Accuracy, simply how often it gets it right, seems obvious. But you're saying it's not always the best measure on its own.
Right. Accuracy is important, but especially for certain types of problems, it can be misleading.
Like what?
Well, to give you the bigger picture, think back to that tumor prediction example, predicting malignancy.
Okay.
In that case, sensitivity, which is the proportion of actual malignant tumors correctly predicted as malignant, is often far more critical than overall accuracy. You absolutely want to make sure you catch as many true positives, the actual cancers, as possible. Missing one could be very serious.
Yeah, absolutely. You'd rather have a few false alarms than miss a real case.
Precisely. Specificity, on the other hand, measures the proportion of negative examples correctly classified so. Benign tumors correctly identified as benign. A high value for both sensitivity and specificity usually indicates a really good model for these critical scenarios.
Okay, so accuracy isn't the whole story. Sensitivity and specificity matter a lot depending on the context.
Definitely.
So how do you make a model perform better once you've trained it, if it's not quite hitting the mark on sensitivity, say?
Well, one effective way is through parameter tuning. This involves adjusting the model's internal fitting options, sort of like fiddling with the knobs.
For example.
For instance, if you're using a k-nearest neighbor algorithm, you might experiment with different k values, the number of neighbors it considers, to find the optimal setting for your specific data.
Trying different numbers of neighbors to see what works best.
Exactly. And then there are ensemble methods. This is a really fascinating approach.
Ensemble, like a musical ensemble.
Kind of. It means combining the predictions of many weaker models. Models that are trained autonomously and might not be perfect on their own, to create a stronger, more robust overall prediction.
Interesting. Strength in numbers.
Precisely. Bagging is a popular ensemble technique. It uses that bootstrap sampling we mentioned earlier to train multiple models, often decision trees. Then it combines their outcomes maybe by majority voting for classification problems or averaging for regression problems.
So you're harnessing the collective intelligence of many simple models to get a better answer than any single one could provide alone.
That's the core idea. It often leads to much more stable and accurate predictions.
Moving on to feature engineering. This sounds important. The sources say it's where the art and science of preparing data really come together.
Oh, it's huge. Our sources emphasize that data scientists spend a significant amount of time on this.
Why so much time?
Because selecting the right features has a critical role to play in the success of a machine learning model. It's all about giving the model the best possible ingredients to work with. Garbage in, garbage out, right?
Right. So what does feature engineering actually involve?
It's basically about transforming existing features or selecting a subset of them. For instance, feature transformation includes techniques for dimensionality reduction.
Reducing dimensions, like making the data simpler.
Exactly. Techniques like principal component analysis, PCA, and singular value decomposition SVD, are common. Think of it like this. Imagine you have, say, 1,000 different measurements describing each customer.
Okay.
Dimensionality reduction tries to find maybe the, 10 most important combinations of those measurements that still capture most of the essential information about the customer differences.
So you simplify the problem without losing the core insights.
Precisely. This is crucial because having too many features or dimensions can make models slow, inaccurate, or just hard to build. It's sometimes called the curse of dimensionality.
Huh. Never heard that term.
Yeah, linear discriminant analysis, or LDA, also reduces dimensions, but it specifically focuses on maximizing class separability, making it easier to tell the groups apart.
Okay, so reducing dimensions is one type of transformation. What else?
Another common one is encoding variables. That's like changing categorical variables, maybe grades like A, B, C, D, into numerical ones so the machine can process them.
Because most algorithms prefer numbers.
Right. Or you might do binning, where you take continuous numerical data like house prices and group them into categories like low, medium, high.
Okay, transforming features. What about selecting them?
Right, that's feature selection.
Yeah.
Here, you're not creating new features, you're choosing a subset of the most relevant ones from the features you already have.
How do you know which ones are relevant?
You need ways to measure relevance. Concepts like information gained from a feature are used. Information gain basically measures how much a specific feature helps reduce uncertainty or classify the data effectively. You pick the features that give you the most bang for your buck in terms of information.
And you also need to worry about features telling you the same thing, right? Redundancy.
Exactly. You need to measure redundancy, understanding if different features contribute similar information. This is done using various distance measures, like Euclidean distance, just the straight line distance, or Minkowski distance, which is a generalization. For binary features, like yes-no, the Jacquard index is common.
Okay.
And for sparse text data, where most values are 0, think about counting words in documents. Cosine similarity is particularly popular. It cleverly ignores all those 0-0 matches and focuses on the pattern of where features do appear together.
So different ways to measure similarity or distance depending on the data type.
Right. And the approaches to actually doing the selection fall into two main camps: filter methods and wrapper methods.
Filter versus wrapper.
Filter methods evaluate features based on their intrinsic properties, independent of the learning algorithm you plan to use. They're usually faster.
Okay.
Wrapper methods, on the other hand, use the learning algorithm itself to evaluate different subsets of features. They essentially try out combinations and see what works best with that specific model.
Ah, so they wrapped the feature selection around the model training?
Exactly. They're computationally more expensive, often much more so, but they frequently lead to better model performance because the features are chosen specifically for that algorithm.
Makes sense. Okay, now let's really dive deep into some of the most popular machine learning algorithms themselves, starting with supervised learning. Classification algorithms, predicting categories. First up, K-nearest neighbor, or KNN.
KNN. This one is often called a lazy learner.
Lazy. Why lazy?
It's called lazy because it kind of skips the abstraction and generalization steps we talked about earlier. It doesn't really build an explicit model during a training phase.
So what does it do?
Instead, it simply stores all the training data. Then, when you give it a new data point to classify, it finds the K training examples that are nearest to it, usually based on Euclidean distance, like literally how close they are on a graph.
Okay, finds its neighbors.
Right. And then it assigns the new point, the class label that is most common, most predominant among those K neighbors. The learning happens right at the moment of prediction.
Huh. Simple idea. Does it work well?
It can be quite effective, especially for certain types of data, but it can become very slow and memory intensive with large data sets because it has to compare the new point to every training point.
Right, I can see that. So if KNN is lazy, what's a more eager learner? Maybe a decision tree.
Yeah, decision trees are quite different. They create explicit rules. What's great about them is they produce very simple, understandable rules. You can literally follow the branches of the tree like a flow chart down to a final decision or classification.
That makes them very interpretable, easy to explain to someone.
Exactly. Very intuitive. But a key aspect of decision trees is dealing with potential overfitting. You need pruning.
Pruning, like trimming a real tree.
Pretty much. You can do pre-pruning, where you stop the tree from growing too deep or complex during the building phase, or you can do post-pruning, where you let the tree grow fully, maybe overfitting a bit, and then you trim back branches that don't actually improve performance on unseen data based on error rates. Post-pruning often works better, but it takes more computation.
So, decision trees are interpretable, but might need pruning. And a single tree can sometimes be a bit fragile, right? Maybe sensitive to small changes in the data.
That can happen, which leads us nicely to the random forest.
Okay, what's that?
This is an incredibly robust and efficient ensemble method. Remember ensembles?
Mm-hmm.
Combining models.
Right, strengthen numbers.
Exactly. A random forest combines multiple decision trees. It builds lots of trees, each trained on a slightly different random subset of the data, and considering only a random subset of features at each split.
So, lots of slightly different trees.
Yeah. And then it combines their predictions, usually by majority vote.
Yeah.
This makes the overall model much more robust and less prone to overfitting than a single decision tree. It's really powerful, especially on large data sets.
What are its main strengths?
Well, besides being robust, it handles missing data surprisingly well. It can balance errors effectively, even in data sets where one class is much rarer than others. And crucially, it even provides estimates of feature importance. It can tell you which features, which pieces of input information were most useful, on average, across all the trees for making the classification decisions. That's incredibly valuable insight.
Very useful. Okay, let's switch gears to supervised learning, regression algorithms. Predicting numerical values now. The simplest form is simple linear regression.
Right. Simple linear regression uses just one predictor variable to forecast a dependent variable. It assumes a straightforward linear relationship between them.
Like drawing the best fit straight line through a scatter plot of data points.
Exactly that. Basic, but foundational.
And building on that.
Building on that, you have multiple linear regression, which uses two or more predictors to forecast the outcome.
Makes sense. More information, potentially better prediction.
Potentially. But a common challenge here is multicollinearity.
Multicollinearity, what's that?
That's when your independent variables, your predictors, are highly correlated with each other.
Ah, okay. Like if you're predicting house price using both square footage and number of bedrooms, those two are probably related.
Exactly. And when that happens, it can make it difficult to interpret how each individual predictor affects the outcome, because their effects are kind of tangled together in the model. The model might still predict well overall, but understanding the why gets tricky.
Got it. Now, what if the relationship isn't a straight line? What if it's curved?
Then you move into polynomial and curvilinear regression. These models can capture those bends and curves in your data by adding polynomial terms like squared or cubed versions of your predictors.
So you can fit more complex shapes.
Right. But you have to be careful with these. If you make the polynomial degree too high, like fitting a very wiggly line, you run a big risk of overfitting the model to your training data again.
Back to overfitting.
Always lurking. It might fit the training points perfectly, but fail miserably on new data.
Okay, this raises an interesting point the sources mention. What about logistic regression? The name has regression in it, but it seems to be used for classification.
Ah, yes. Logistic regression is unique. It's often considered both a classification and a regression technique, which can be confusing.
How can it be both?
While it's called regression, its primary goal is actually to predict the probability of a categorical outcome, usually a binary one, like 0 or 1, yes or no.
Okay, predicting a probability, which is a number between 0 and 1.
Exactly. Instead of fitting a straight line, like linear regression, it uses an S-shaped logistic function, also called a sigmoid function, to model these probabilities. It squishes the output neatly between 0 and 1.
Ah, so the output is a number, probability, but it's used to classify based on whether that probability crosses a certain threshold, like 0.5.
Precisely. And to find the best fit for this S-shaped curve, it uses something called maximum likelihood estimation, or MLE.
MLE.
At its heart, it just means finding the parameters for the logistic curve that make the observed data most likely or most probable to have occurred under that model. It's a bit more complex mathematically than just minimizing distance like in linear regression, but it's the standard way to fit these probability models.
Okay, so logistic regression predicts probability for classification. Got it. Now let's move beyond supervised learning. We also have unsupervised learning algorithms. No predefined labels here, right? Just finding structure.
Exactly. The goal isn't to predict a known label, but to find hidden structures, patterns, or groupings in the data itself. K-means clustering is one of the oldest and most popular techniques for this. It's centroid-based.
Centroid-based.
Yeah. With K-means, you first have to decide K, the number of clusters you want to find in your data. Maybe you think there are 3 distinct groups of customers, so K3.
Okay, you specify the number of groups.
Right. Then the algorithm works iteratively. It randomly places k initial centroids. Think of them as the starting centers of your clusters. Then it assigns each data point to the nearest centroid. Then it recalculates the position of each centroid based on the average position of all the points assigned to it. And it repeats this. Reassign points, recalculate centroids, reassign, recalculate, until the centroids stop moving much, or the assignments stabilize. The aim is to end up with clusters where the points within each cluster are very similar to each other, close to their centroid, while the clusters themselves are as different, as far apart as possible. Maximize homogeneity within clusters, maximize differences between them.
Simple concept again, but sounds powerful for finding groups you didn't know existed.
It really is. Very widely used.
Okay, another unsupervised technique mentioned is association rule learning, often used in market basket analysis. What's that about?
This one is all about identifying interesting relationships hidden in large data sets. Retailers commonly use it for cross-selling.
Cross-selling, like suggesting items that go together.
Exactly. Think of it like this. The algorithm might discover a rule like bread, milk, egg.
Meaning?
It signifies that customers who buy bread and milk often also buy eggs, finding these kinds of co-occurrences.
I see. So the retailer could put eggs near the milk, or maybe offer a discount if you buy all three.
Precisely. That's the practical application. The a priori algorithm is a clever bottom-up approach, often used here, to find these frequent item sets, the groups of items frequently bought together.
How does a priori work? It must be hard to check all possible combinations of items in millions of shopping carts.
It would be impossible brute force. A priori uses a smart principle. If an item set, like peanut butter jelly, is infrequent, then any superset containing it, like peanut butter jelly bread, must also be infrequent.
Ah, okay, so you can prune the search space early.
Exactly. It starts by finding frequent individual items, then uses those to build frequent pairs, then frequent triplets, and so on, discarding infrequent sets at each step. This saves a ton of computational effort.
Clever.
Then once it has the frequent item sets, it generates potential association rules from them, like our bread milk egg example. And finally, it filters these rules based on metrics like a minimum confidence threshold.
Confidence meaning?
Confidence is basically asking, if a customer buys bread and milk, how likely are they also to buy eggs? Is it 80% likely? 50% likely? The retailer sets a threshold, say, only show me rules with at least 60% confidence to focus on the relationships that are strong enough to be potentially useful.
Fascinating stuff. Okay, let's look towards the bleeding edge now. What about artificial neural networks, ANNs, and deep learning?
Right. This area is heavily inspired by the structure and function of the human brain, with its billions of networked neurons, allowing for massive parallel computing.
That biological inspiration seems key.
It is. It helps these networks tackle incredibly complex tasks involving perception and pattern recognition that are very hard for traditional algorithms. Think about a cricket fielder making an incredible catch that's a complex calculation based on trajectory, speed, wind, past experience, anticipation. Neural networks try to mimic that kind of complex, learned response.
So what's the basic building block?
The simplest form of a neural network is the perceptron. It's a single neuron that takes multiple inputs, applies weights to them, sums them up, and then uses an activation function to produce an output, often classifying inputs into one of two classes using a hyperplane as a decision boundary.
A hyperplane, like a line in 2D or a plane in 3D.
Exactly, but often in many, many dimensions.
Okay, so that's the simple version. What makes them more powerful?
When you start stacking these neurons into layers specifically, when you have one or more hidden layers between the input layer and the output layer, you get multi-layer neural networks.
Hidden layers?
Yeah, they're layers where the neurons aren't directly connected to the outside world, the input or the final output. They learn intermediate representations of the data. The learning process involves deciding on the architecture, how many layers, how many nodes, neurons in each layer, how signals flow, and crucially adjusting the connection weights between neurons.
How do they learn the right weights?
Backpropagation is the most common training method. It's how the network learns from its mistakes. When the network makes an incorrect prediction, the error is calculated at the output layer. Then, that error signal is propagated backward through the network, layer by layer.
Okay.
And as it goes back, it's used to calculate how much each connection weight contributed to the error, and then those weights are adjusted slightly in a direction that should reduce the error next time.
So it's like feedback, telling the connections how to change.
Exactly. It's like a coach telling a player exactly what adjustment to make after a missed shot so they can improve next time. It's iterative, often requiring many passes through the training data.
And when these multi-layer networks have lots of hidden layers?
Then they become deep learning networks. That depth allows them to learn hierarchical representations of data, finding simple features in early layers and combining them into increasingly complex features in deeper layers.
And that's where the magic happens for things like,
Advanced image recognition, understanding natural language, speech synthesis, tasks that require understanding very complex hierarchical patterns. But this power comes with a trade-off.
which is,
It's computationally very expensive. Training these deep networks requires massive amounts of data and huge amounts of processing power, often needing specialized hardware like graphics processing units, GPUs, to handle the calculations in parallel.
right, not something you can easily run on your laptop.
Not usually for cutting-edge models, no.
Okay, what about representation learning? The sources also call it feature learning.
Yeah, this is closely related to deep learning, actually. It's about algorithms discovering useful representations or features automatically from raw data, especially for complex real-world objects like images, audio, or video, instead of humans having to carefully engineer the features.
Like we discussed with feature engineering.
Right. Representation learning aims to let the model learn the best features itself as part of the training process. Techniques like autoencoders and independent component analysis, ICA, are key here. Autoencoders, for instance, try to learn a compressed representation of the input by forcing data through a bottleneck layer and then reconstructing the original input. The compressed representation often captures the most salient features.
So letting the machine figure out the important inputs.
That's the goal. And then there's active learning. This is a type of semi-supervised learning.
Semi-supervised, meaning it uses both labeled and unlabeled data.
Exactly. But what's unique about active learning is that the algorithm can interactively query the user or an oracle for labels on new data points.
It asks for help.
Yes, but strategically. It focuses on asking for labels for the data points where the model is currently least specific or most confused, the points it thinks will give it the most information to improve its performance.
So it tries to learn efficiently by only asking for labels on the most useful examples.
Precisely. It can significantly reduce the amount of manual labeling needed, which is often a huge bottleneck in machine learning projects.
Very clever. Now, all this incredible power, all these techniques, it brings us inevitably to a crucial question the source material raises: ethics.
Absolutely crucial. Our sources point out that machine learning is still relatively new and still evolving, and maybe the biggest fear and issue revolves around privacy breaches.
How so?
They note that analyzing data, especially data about people, can potentially reveal private enough facts, things about health, habits, beliefs that individuals may not want shared, even if the individual data points seemed anonymous at first.
Right. Combining different pieces of seemingly harmless data can sometimes paint a very revealing picture.
Exactly. And people have very different preferences for sharing information, right?
Yeah.
Some things are okay publicly, some only with friends, some only with family. ML doesn't inherently understand these nuances.
So the potential harm comes when...
When ML algorithms use this potentially sensitive information, maybe for things like preference-based customer segmentation to send highly targeted marketing, or perhaps even for decisions about loans or insurance. The sources warn this could hurt the emotion of people and actually do more harm than good, potentially even leading to legal actions.
So it's not just about technical accuracy, but about the impact of using the technology.
Absolutely. The sources stress that critical consideration is required before applying ML and especially before using any outcome derived from it. We need to think about the potential consequences.
And there you have it. Wow. We've covered a lot in this deep dive into machine learning, from its philosophical underpinnings, how machines kind of learn like us, to its ubiquitous practical applications, the distinctions between key algorithms like classification and regression, unsupervised learning, the whole feature engineering piece.
And the cutting edge with neural nets and deep learning.
Right. And wrapping up with those critical ethical considerations that really must guide its development and deployment.
Hopefully this has provided you, our listeners, with a clearer conceptual understanding of machine learning, maybe making you feel a bit more well-informed and perhaps even excited about its immense potential.
And also aware of the important challenges it presents.
Exactly.
So what does this all mean for you? Our sources remind us that no man is perfect, and maybe more importantly here, the same is applicable for machines. They emphasize that incorporating human intervention is the recipe for the success of machine learning. Given this need for human involvement and oversight, what role do you think human judgment and ethical considerations will play, or should play, as machine learning becomes even more deeply integrated into our daily lives? Something to think about.
Thank you for joining us on Book on Focus. Until next time, keep learning and stay inspired. If you enjoyed this episode, we'd love your support. Subscribe to our YouTube channel, leave a like, and share with others who are passionate about growth and technology. Your engagement helps us bring you even more insightful content. See you soon!